David Brubaker is all about openness. He holds the door open for people, he opens the super sealed jar of pickles, and now he's working to open radio access networks and virtualize 5G. Two things that are even harder to open than that jar of pickles. If I'm being honest, I'm not even really sure what that means, but David is a senior product line manager for Xilinx's Zynq UltraScale Plus RF SoCs that are at the heart of this. And he's been working on wireless networks since before we numbered their generations. So he's going to explain what it means, why it matters, and how it's being done. Welcome to Tech Chats, David.
Thank you, Chris, and thank you for that introduction.
All right, so to start off, can you just explain what a radio access network is and some of the changes we're seeing as we move from 4G to 5G?
Okay, I'm glad to, and I'll probably go back a little bit further than even 4G because they're actually a little bit different. But we'll start with that, and I'll talk a little bit of the differences. First of all, we talk about 5G. Everybody talks about 5G, and G actually stands for generation. And there was actually the first generation, second generation, third generation, 4G, which people also know as LTE or LTE Advanced. And now the latest is 5G. But each of these generations in the network are very different on how communication, whether it be an SMS message or voice message or data download, get from, let's call it the infrastructure, the mobile network, all the way to your phone. And so when you look at 4G, one of the key differences between 4G and 3G is that 3G is what we call circuit switched, and that means we had a dedicated circuit like a wire between your phone and what we call the switch. Well, 4G was what we call packet switched. And in this particular network, it's more like an internet transfer where packets are transferred, say, from a mobile core or a network all the way to your phone. And this is very different than circuit switch. But 4G was the first packet switched network. And what was interesting about the architecture is we would refer to the mobile core or the internet. That would be where you would get your data from. And there were two boxes in the 4G network. We called them the BBU or the baseband unit, and then the RRU for remote radio unit. And these things were physically separate boxes located in different locations, and they were typically connected via optical fibers. And so the baseband unit did, let's call it about half of the processing within what we would call the stack of the network. We would call that layer 1, 2, and 3, for example. And then the CPRI was a common public radio interface. It was a standard interface that connected the BBU to the radio unit. And what most people see is the remote radio head. This is the thing that's up on a tower with the antennas radiating over to your mobile units. So this is the 4G network. Now, when you go to 5G, there are certain things that we want to achieve in 5G. One is faster download rates, okay, so you can have broader, faster connections. The other thing in 5G is what we call lower latency, and this is for, the use case that's touted as autonomous driving, but also smart factories. And then the other one is what we call massive connectivity, where there can be many, many types of devices like cameras and so forth connected on the network. The 4G network wasn't built for these new features, and so we had to design a completely new network and call that 5G. In 5G, we still have the mobile core on the left, but now we have what we call a GNB or CU for central unit. And then we have a distributed unit, and we have a radio unit. If you look at that, the radio unit is very similar to the remote radio unit that we had in 4G. It's actually up on a tower somewhere. There's multiple types of radio units. There's a macro, there's massive MIMO, and even millimeter wave type remote radio units. The CPRI has been kind of renamed what we call Fronthaul, and that's because the actual functions that we do in each one of these boxes is now changed. And this addition of the distributed unit is what we call disaggregation of the radio network. And this is a little bit more detail on what functions that can be done within the 5G network. And you'll see the mobile core again, and you'll have the centralized units, the distributed units, and then the multiple radio units, and of course the end users. Now, the distributed unit does some of the lower layer processing, and I'll show you that in a few slides so you understand the functions we do there. But this distributed unit can actually be co-located with the central units in like a server farm or a data center, okay? It can be located between the data center and the radio units, or even located within the radio units. The 5G architecture allows these functions to be placed anywhere, and that's so they can meet different needs depending on the end-use application. And one of the things we're going to talk about today is the distributed units, primarily with what we call the T1 Telco card, which does some of the functions and how that's done within the radio network. Okay, so the key point to note is, that 5G has a different architecture. We've added what we call a distributed unit to the network that can be physically located in different locations, depending on what the operator actually wants to implement.
So we have this new architecture and these different units. So how does that factor into the topic of virtualization? And what is virtualization in 5G?
Okay, well, that's a great question. Virtualization actually kind of started with 4G, but it's actually really taking off with 5G. And if we take a look at the traditional LTE model, what actually happened is the operators would buy hardware from what we called OEMs. And what they would do is they would design that BBU and they would design the RU with custom silicon that would implement those functions that I referred to within the network, and then build their hardware to make this endpoint-to-endpoint connection from the radio unit all the way back to the baseband unit or the mobile network. But even though there was an intent to make the hardware interchangeable, it never really worked well. And so this thing created this vendor lock. And once an operator picked a vendor, they were locked into that vendor. They couldn't move away. And it also made it very difficult for operators to deploy what we call software services. This is a big feature of 5G and virtualization. They can range from things like location, video distribution, and things. They can't do it. And that's because this hardware is all custom designed and has to be done pretty much on a one-off basis. So what we have is a thing called virtualization. And in virtualization, all of these functions, or as many functions as possible, are what we call virtualized on the BBU or the baseband unit or the CU. And that means they're actually not implemented on custom hardware. They're implemented on standard servers, standard x86 processors, and implemented in a software environment rather than a pure hardware platform like an ASIC. The first thing that happens is because the hardware is somewhat standard, it lowers the overall cost of the network. Okay, and with the fact of this distributed unit, which we talk about, we actually what we call virtualize the baseband function. Okay, so rather than being implemented in pure hardware, either FPGA or ASICs, it's implemented again on Xeon processors, and you create what is kind of an open platform so that the hardware can be provided not only by, say, tier one OEMs, but different people can implement and the hardware on these standard servers, and then create what they want to provide as a software service. In particular, moving these softwares to the edge. And what we call the edge means is this distributed unit where we can have processors there, and they're not actually located all the way in the data center. So in summary, virtualization is a technique where the functions of the network, particularly up to the distributed unit, are implemented on servers and virtualized, so it's not custom hardware. Okay? We can take another look at that in a little more detail. You can look at a traditional baseband unit on the left, and it would be provided from OEM, and it's really just a box, okay? And then we have a virtual VBBU distributed unit on the right. So they kind of both look like boxes, so you kind of have to kind of peer inside to see what's different about the two. And if you take a look at those, the main difference is that in the traditional BBU, you have several chips and functions that do the things. There's always a CPU where it can do certain things, but there's two functions, and I've talked about them before. The Fronthaul, that's that connection from the distributed unit all the way to the radio unit. And then what we call L1 baseband are the different things, and essentially it does things like forward error correction and HARC and different things that have to happen very quickly within the system, and they don't really do very well on a CPU, which can get tied up doing software functions. So the traditional BBU, those were implemented in ASICs, and they became custom hardware. Now, what happens in the virtual BBU, we actually now use a Xeon server for the CPU, and we do a lot of those functions in the CPU, but we actually have dedicated FPGAs, or field programmable gate arrays, that are optimized for the Fronthaul and the L1 functions. And they're actually implemented in what we call PCI cards. So this allows, an operator to build an entire DU and CU functions out of standard servers and then plugging in what we call a PCI card into a slot. And then those functions that are typically best suited to hardware implementation, like what we call the Fronthaul and the layer 1 processing, are implemented on FPGAs. And then typically either our customers or Xilinx will offer the hardware bit file that needs to be put on to the L1 card as either our IP, or sometimes customers will have their own IP that they want to put on those cards. So we can take a look at actually what is in what we call a T1 card. We're going to go into a little more detail here on the T1 card, but essentially it's a PCI form factor, as you can see. And the functions that we do inside this T1 card, and remember, we actually have typically 2 FPGAs on a card that we would offer. One FPGA would do the Fronthaul, that's the connection to the radio unit, and the other one would do what we call layer 1 offload, which does the forward error correction. And we call that low density parity check for 5G LDPC. And then in LTE, because you actually have to implement still legacy LTE in your system, that's turbo. And we also do polar on that card. So this is a card that is a standard offering by Xilinx and can plug into any server. And then they can implement an entire DU in one of these server chassis. Okay. It's also important to note that we actually offer validated reference designs that can interface to the standard servers, FlexRAN, and we use what we call the DPDK for Fronthaul. That's a standard interface. These functions, as I've mentioned, the layer 1 offload and the HARC offload and the Fronthaul are very time critical functions. They have to happen at a certain time, and therefore they're better implemented on hardware.
And is this hardware modularity, is that where the idea of Open RAN comes from?
Partly. There's 2 functions to Open RAN. Open RAN is actually started slightly differently. Again, the Open RAN concept was conceived to try to remove vendor lock-in and create standard interfaces between different functions of the network. So I think the best way to kind of talk about Open RAN together is if we go down and look at what we call the ORAN stack. And what does T1 offload from the CPU that we've talked about. So here I'm showing, what we call the ORAN stack. If you look at it, you have a variety of functions that would happen in the DU, as shown there in the blue box. And you can see the ODU, and then the ORU stands for Open Distributed Unit and Open Radio Unit. So this is the concept of open. So the first part of Open RAN is deciding if you're going to create an open distributed unit and an open radio unit, where do you split the boxes? Okay, you can see split 7.2, okay, and then you'll see split 6 at the top. And so the first part of Open RAN is defining where that split is. And of course, the Open RAN defined that it's what we call split 7.2. And in that function, the radio unit does certain functions. For example, we do the pre-coding, what we call resource element mapping, and in really particular of interest is what we call the IFFT, the inverse FFT, and the FFT functions, okay? Those are all done in the radio unit. Traditionally, in 4G, that split was at what we call split 8, showing there. So all those functions that are between split 8 and 7.2 were actually done in the BBU in LTE, and now they've moved into the radio unit. So the first part of Open RAN is defining this function of these functions of where you're going to split it physically in the data path. The other part of Open RAN is actually probably the more complicated part, is that as you're doing this data and you're doing certain control and telling the radio unit what to do, you have to have certain software APIs that are common, so that anybody who implements an open radio network can know how to communicate to a radio unit to tell it what to do. And those things can be, exactly what FFT settings to be, what your beamforming can be. There's many things that now the radio unit that traditionally in the LTE network was not very sophisticated on the types of things and functions that it had to do and decisions it made in the network. That was all done in the BBU. So ORAN, in my mind, has 2 major functions. One is defining where that physical split is in that interface physically, and the other one is the software APIs and control functions that are passed between the DU, the OU, and also the CU, okay?
Now, these are obviously very complex systems, but you mentioned that you already have a reference design. So can you talk more about that?
Yeah, absolutely. So we do actually offer turnkey reference designs. Some customers may want to design their own, but that's a lot of work and validation. So we have our own reference design that actually uses an x86 interface with an industry standard software framework. And all the key baseband APIs or application programming interfaces that are standard as part of that ORAN interface, we develop that and provide that. And then we have a card, and it has what we call QDMA drivers. And these are the standard acceleration for the card. And then you get this full reference design that can be put on your T1 card as a turnkey solution. Okay, so that's part of it that happens in what we call the layer 1 offload. And that actually is implemented in what we call the ZU21DR. That's a device in our RFSoC family. So it's a completely turnkey solution to do all what we call layer 1 offload. And then if you take a look at the Fronthaul, is that, as I've alluded to, that interface between the DU and the RU. And I've already mentioned that in Open RAN, not only is it the physical interface, the data transfer, but it's also got all kinds of software commands and APIs that have to go between the two in what we call typically the control plane. And so those commands are standardized. And so we actually have APIs for all of this network function virtualization or NF software. And again, the drivers are there. Now, there's a couple key things that the Fronthaul interface has to do. Number one, it actually has to transmit the data. Okay. So it actually will transmit the data, and it has to transmit, the control plane. But the other thing that it has to do is it actually has to transmit exact time and frequency, because, the whole network operates on the fact that it's going to transmit at a certain time and it knows the frequency exactly. And when we go back to what we call that 7.2 split, that timing information is not as defined as it was in what we had split 8 with LTE. So it actually has to transmit extremely accurate time stamping and frequency so the entire network can be synchronized. So these are the functions that are implemented on the Fronthaul reference design that we provide also.
Now, obviously, if you build something, you test it and prove it out, right? So let's talk about the performance metrics that you have.
Yeah, that's a good point. And, it is possible to implement all of these functions with a Xeon core. And so I've got kind of a performance comparison using the T1 card on a Dell R740 server. This is a server we have, so we tested it. So, for example, I've got here the demonstrated performance of a T1 card using the Dell R740. And on the left is everything, just a standalone server with no T1. And you can see that function we're doing there. This is everything from the MAC all the way down to what we call the PTP timing function. And you can see there on the left that our throughput is about 718 megabits, and the latency is 45 microseconds. And the decoder, which is actually the harder function to operate, it's only 183 megabits per second at 62 microseconds latency. Okay, now if you look over on the right, which is the red boxes, you can see by adding a single thread neon and one T1 card, we're actually getting a 17 gigabit throughput with that particular function and 7.8 gigabit on the decoder. And you can see the latency is significantly lower. It's about over 3x lower latency and the higher throughput. So what this means is that, with one core, we can do a lot more radio processing and allow a lot more data over the air and processing than you could do with the function implemented in software. Now, the Fronthaul is a similar case. We talk a lot about Fronthaul as the number of transmit and receive. These are the number of antennas for each radiating antenna. So we have what we call 4T, 4R. That's 4 transmit antennas, 4 receive antennas. And then we talk about occupied bandwidth. So how many carriers can we put in 100 megahertz of bandwidth? And so if you were to look at that Fronthaul with 2 sectors, it would take something like 24 Xeon cores to actually do that Fronthaul interface. If you were doing 4 sectors, it would take 64. Okay. Again, looking on the right for the same function, we can do that with 1 Xeon core for 2 sectors or 4 sectors and 2. So the functions that we implement in hardware are best done in hardware. Okay. So the big advantage here with the T1 is we can see, one, much higher throughput on the L1 processing and lower latency, and then also much higher bandwidth available on a single FPGA compared to multiple Xeon cores. So that actually results in lower overall cost to implement the virtual baseband unit. This is actually kind of a new offering, the T1 Accelerator card. It actually has two FPGAs on it, what we call ZU19 and ZU21. It actually accelerates the key functions in a virtual baseband unit that are needed in the network to improve capacity, okay? And it does it without doing a custom ASIC, so it allows anyone to build a virtual baseband unit. You can plug this card in and get essentially state-of-the-art performance with a turnkey reference design and a standard ORAN format. And so this is actually an innovation, in the 5G network where it allows operators to, one, virtualize the hardware with a standard interface, okay, with this ORAN interface, so it becomes kind of vendor independent, and it will lower the overall cost of the network, but also allows them to offer more services. And that's the key function of it. This is a trend that is going to happen through the 5G network, and we're already seeing it right now.
Alrighty, thanks, David. And once again, that's David Brubaker from Xilinx. If you'd like to learn more about ORAN, 5G virtualization, and the Xilinx FPGAs and RF SoCs that make it possible, click the links in the description or visit Mouser.com. And be sure to check back soon for the next episode of Tech Chats.